So for your calculations, I already have here like some things annotated, especially the numbers that I'm writing for each one of the things that we need to calculate or the experimental data that we have. So to start with, the type of metal used for the cathode, in this case, it's aluminum. And another thing that we need in order to complete the calculations is the number of amps that we're using as the current in the power supply. So for this experiment, we're using the power supply and the voltage is set up at 3 and the current is set up at 0.2. So we have the units for that current in amps, and 1 amp is the same as 0.20 coulombs per second. So I'm using the coulombs per second because we need that number to actually calculate the charge that it's being transferred. And to calculate the charge that it's being transferred, that charge, it's going to be in units of coulombs. So you have the mass of the cathode, mass of the anode, which is the copper, and for the cathode, what we have is the metal aluminum. So number 3 is the time that the experiment is running for. So we're using something close to 25 minutes, but we need that number in seconds, so we can use that amount of time to calculate the charge transfer. So the first calculation that we have to actually do is get that charge transfer, how much charge is being transferred in the experiment. So to get that number, what we're doing is multiplying the current times number 3, which is the time in seconds. So I'm giving you the example with the time that we have in trial 1, and just for you to see what's happening with the units. So the unit second is canceling out, and the number that you're getting right there will be a number in units of coulombs. Now, number 5 and number 6, that's experimental data. You weigh your metal for the cathode, the aluminum, before and after the experiment. So the initial amount is what we have in number 1, and then after your 25 minutes for the experiment, you have the number that we have listed right there in number 5. Okay? So it's a mass after the experiment is completed. Number 6, again, it's another experimental data. You have the initial mass of copper, which is the metal that we're using in the anode. Now, after the 25 minutes, roughly 25, a little bit higher than that, the mass that we have now is 4.182 for trial 1. So you can look at your numbers here. The mass of the copper is decreasing. The mass of the aluminum is increasing. In the experiment, what is happening is that your ions of copper are being reduced to copper solid. That copper as a solid is going to cover the aluminum. Okay? So you're creating this layer of copper solid on top of the aluminum. So the initial mass of your copper, the solid that you have initially there, it has to decrease because it's being used up, right? Your copper as a solid is going into solution to copper ions, and the ions are being reduced to give you copper solid on top of the aluminum. That's why the mass of your copper is decreasing. The mass of the aluminum now it's increasing because it's being plated with a layer of copper. So we can calculate like how much the mass of the copper is decreasing by how much, just the difference between your two numbers. So you have for the mass lost by the anode, we're doing your mass of the anode initially is what you have in number 2. And then after the experiment is what you have in number 6. So the difference between those two numbers is going to tell you how much copper is being lost by the anode, which is your piece of copper metal. To determine how much copper is being plated on top of your piece of aluminum. So you have your initial mass for aluminum, it's what you have in number 1, right? After the experiment, that number is going to what you have in number 5, mass of cathode after deposition. So you see your number is increasing. If you want to know how much copper is being plated on top of that piece of aluminum that you have, we can do the number that you have in 5, right? Number of what you have in 5 is the mass of your aluminum, right, with the layer of copper on top, minus what you have in number 1, and what you have in number 1 is your original piece of aluminum, just aluminum. So the difference between those two numbers is going to tell you how much copper it's been deposited on top or plated on top of the aluminum. Now number 9, it's like in theory how much copper you can plate on top of the aluminum using that specific current that we have right there, and for that period of time that we're running the experiment for. So we're running the experiment for like roughly 25 minutes or a little bit more than that. So we're starting our calculation with the number that we have in 4, which is the charge that it's being transferred. And remember, we're calculating that charge by multiplying the current that we're using times the time in seconds. Okay? So we're starting with the number that we have in number 4, which is a number with units of coulombs. Now, what we have after that, it's like every mole of electron contains a charge equal to 96,485 coulombs. So that number right there is the charge per electron, per mole of electrons. So when you do your number 4 times that conversion factor right there, your coulombs are canceling out, and what you have right now is the number of moles of electrons that are being transferred in the experiment. Second conversion factor, 1 mole of copper over 2 moles of electrons. So I'm going to show you why we're using that right there. Every ion of copper plus 2, it's been reduced to copper solid, right? Because you're forming this solid layer on top of the aluminum. So for every mole of copper that you have, right, every mole of ions of copper requires 2 electrons to become copper solid. So that's why we have 1 mole of copper over 2 moles of electrons. Every mole of copper needs 2 moles of electrons to go from copper plus 2 to copper solid. Now you are trying to calculate an actual mass. So the third conversion factor that you have in that calculation right there is just the molar mass of copper. Okay? When you're done here with the second conversion factor, Mole of electrons is canceling out, and what you have, it's a number in units of mole of copper. So you can convert moles of copper to grams of copper by multiplying times the molar mass. So that's what we're doing with that third conversion factor right there. So that's going to tell you the expected amount of copper, or like the amount of copper that you're expecting to plate on top of the aluminum when you're using a current equal to 0.2 and you're running the experiment for roughly 25 minutes. So that's the theoretical amount. Now for number 10, number 11, this is very easy because we have all the numbers that you need to plug in your equation. To find out the plating efficiency based on current, we're doing what you have in number 8, which is the mass of copper plated, and that's the same number that we're using for number 11. So the mass of copper plated divided by that theoretical mass that you're calculating in number 9. Okay? So remember, the mass of copper plated is your experimental data. You have the piece of aluminum with the layer of copper on top, right? And the mass difference for your aluminum is telling you how much copper was plated. So that's your actual yield, let's call it like that, right? What you're actually getting after you're done with the experiment. What you're calculating in number 9 is your expected amount. So you're expecting to get that number, but you might have something a little bit different because things can happen while you're performing the experiment. So when you do your 8 divided by 9 times 100, that will give you your plating efficiency based on current. And then the last one here, you're calculating the plating efficiency based on mass difference. So for this one, we're also using the mass of copper plated. And now we're dividing that number by what you have in number 7, mass lost by the anode. So the mass lost by the anode, right, is the amount of copper that is being transferred. So you should be expecting that your theoretical value, right, that's the amount that you're expecting to plate, that number should be the same as the mass of copper plated. Right? If your copper solid is losing X amount, it's because that X amount is going to plate the aluminum, right? That's the expectation, but your two numbers are probably different from each other. So that's the last thing that you have to calculate, the plating efficiency based on mass difference. So you have the mass of copper plated in number 8, and you divide that number by the mass lost by the anode, which is your piece of copper, times 100, and that will give you that percentage.